Hello all. So this is my second video, and after making a first video, you guys have given a lot of inspiration, and I am really motivated by your feedback and by seeing that a lot of people appreciated my first video. So thank you very much. And guys, please keep writing to me so that I get motivated to make similar kind of video. And if you like the contents and topics, please subscribe to this channel so that you can know my next video as soon as it's available to view. So again, now let us start. So today we are going to discuss about the loss calculation in magnetics. How do we calculate the losses which happens in the magnetic component? So today we will cover the two topics under the power supplies, different SMPS, and basically this knowledge which we are going to discuss today, this is not readily available in the books. It's actually through my experience and my learnings which I have done in last 15 years working in this field. So let's start. So today we are going to discuss about the inductors and transformers. So different kind of inductors which are used in power supplies. Uh, they are under various categories. So we will go one by one. First is the PFC boost, buck boost inductor. Second category is the inverter output inductor. Third is the filter inductor for battery current. And fourth category is the differential mode inductor for input current. Then output filter in LPS power supplies, flyback, charger, etc. And common mode chokes for EMI filters, and small inductors in DSP power supplies. Under transformers, we will discuss like power transformers, which are the small scale transformers, charger, low power supply, etc. Then signal transformers, basically potential transformer for voltage sensing, and then current transformers, which usually called as the CT. So for inductor, let us discuss that what are the important parameters which we should consider for inductor design, as we saw in the previous video. So first is the maximum flux density. How much flux density we should consider so that our components operate perfectly fine. And second is the losses. So we are going to discuss that what kind of losses occurs in the inductors. One is the low frequency copper losses, which we call as a DC losses, and second one is the high frequency copper losses, and then core losses. Next is the core temperature. So we have to be very cautious about the core temperature when the inductor works in actual power supply, how much it is going to heat up and what is the allowed limit. Then winding temperature. These are the very important parameters which we will discuss in details in the coming slides. And then physical dimension, how we are going to mount this, and how the dimension need to be defined. And then the insulation systems, so what insulation systems have been used, and different insulation systems will have the different limits of temperature, so that we are going to discuss. And next we will also discuss about the regulatory requirements, which is basically UL and IC. So in inductor, usually powder iron core for low power system, mostly which I have worked, and for wherever we are having high DC currents. So we use this core, which is 26 mu permeability. The the 26 mu permeability core is having the good characteristics for the DC bias. So wherever we see that the DC current is high for the inductors, we can use this 26 mu core, and there are different permeability cores available with the supplier. So we can go back to the supplier data sheets and we choose as per our design how we have designed these inductors. So this is a very important graph which shows here the permeability versus the DC bias curve. So under the DC magnetizing force, which is basically H, under different DC magnetizing force, how the permeability is changing. So this is going to give us the information that up to what current our inductors will not saturate and how will be the saturation patterns. And this is the core loss density basically for this particular permeability core. So under different flux density which we have chosen for the inductor design, how will be the core losses, and to plot this graph, these are the formula which is being used. The next is the maximum flux density. So how do we calculate the maximum flux density? And with respect to flux density and magnetizing force, with increasing magnetizing force, how the flux density changes. So this is shown here. And flux density we can calculate using the below equation. So this is the L nominal inductance nominal will be calculated based on the AL value and the number of turns square. If we will do this, we will get the L nominal. And now we have to calculate that what will be the HI magnetizing force at different current. So once we know the number of turns, we multiply by number of turns to the current and divide by the magnetic path length. So we will get the HI forces, and then with this HI we can find out that what will be the inductance drop at this magnetizing force, and then at particular current what will be the inductance. We can now find out that L nominal, if we multiply by this L drop I, so we will get the inductance value at that current. And then that's how at that current what will be the flux density. We can calculate the inductance at that current, multiply by the current divided by the number of turns into the cross-sectional area of the core. So in the previous video we have discussed about the core cross-sectional area. So this is coming from there. If somebody want to know more about the core cross-sectional area, they can see my previous video, and there you will get more information about the core cross-sectional area. So this is the abbreviation which we have defined here. AL is the value given in the core data sheet. Basically this AL value you will get in the supplier core data sheets, which will be different value for different permeability. H is the magnetization force in the Ørsted, which is how this is calculated here. L drop is the drop in the inductance as a function of DC current, and A is the cross-sectional area of the core. The next is the losses, so which we discussed that there will be two kind of losses. One is the low frequency copper losses, then high frequency copper losses, and then core losses. So the different patterns of current will be there under different category of components. So here we are taking the examples of the PFC inductors. So PFC inductors basically have the two component of the current. One will be the 50 or 60 hertz components of the current, and then another will be the high frequency current, which will be riding on this low frequency current. So if we have to calculate the losses, we need to calculate the losses at the low frequency copper losses and then high frequency copper losses. So first we need to find out that what is our different value of the current at the low frequency and at the high frequency, and then that current multiply by the our DC resistance and our AC resistance, we will get that losses. So basically here the low frequency copper losses, how do we calculate? Low frequency losses is equal to the I square LF. So basically I square LF is the IRMS of low frequency into RDC at particular temperature, and then RDC at certain temperatures, we know that RDC at 25 degree into 1 plus T minus 25 degree into alpha. This is the coefficient of the temperature coefficient. So we can calculate the RDC value at the particular temperature, and by using this formula we can calculate the value of low frequency losses at certain temperature. Then high frequency copper losses, how do we calculate? So P high frequency losses will be calculated I square RMS high frequency current into RAC at particular temperature. So RAC at particular temperature, how it will be calculated? It will be RAC underscore T will be equal to RDC underscore T multiplied by the KAC. KAC is the skin and proximity effect multiplication factor, and RAC is the AC resistance of the winding at temperature T. RDC is the DC resistance of the winding at temperature T. So this is how we will calculate the high frequency losses. And here is the factor which we have talked in the previous slide. So KAC is the skin effect factor. This is how do we calculate the skin effect, and this is the proximity effect factor, and these are the delta is the skin depth. It's skin depth how we calculate by using this formula at the particular switching frequency. Suppose our switching frequency is the 15 kilohertz, 16 kilohertz, 20 kilohertz, 30 kilohertz. So at different frequency the skin depth will be different, and this is the proximity factor. This is how do we calculate, as is the equivalent thickness in the square of the conductor. Next, we are going to discuss about the core losses. So how do we calculate core losses? Core losses basically are two types of losses. First is the hysteresis loss, another is the eddy current losses. So we will go one by one. The hysteresis loss is how we calculate P core is equal to the delta B, B square into switching frequency 1.46 into the volume of the core. So this is the formula basically which is given by the core manufacturer, who defines that at for particular core how the core losses should be calculated. And here delta B is the change in the flux density in switching cycle, FSW is the switching frequency, B is the volume of the core. Then P core equal to 1 upon count summation I is equal to 1 to count P core. So P core is the core loss per line cycle. So this is the empirical formula which is given in the supplier data sheet. And next we are going to calculate the flux density swing. So how to calculate this? So in case one, if the current ripple is small and the change in inductance is neglected, then delta V we can calculate directly L nominal, L drop into delta I of the inductors upon number of turns of the inductor into the cross section area. In case 2, if the current ripple is large and change in inductance is considered, then I1 will be I plus delta I by 2 and I2 will be I minus delta I by 2. So delta B1 we can calculate like this and delta B2 like this, and then delta B equal to delta B1 minus delta B2, which we can see here in the hysteresis loop. Next we are going to talk about the core temperature measurement, how to measure the core temperature. So permeability versus core temperature. If the core temperature rises, because when there will be the losses in the inductors, so definitely this losses will be dissipated as a heat of the component and the component temperature will increase. So if the temperature increase, then here is the graph which shows that how the permeability change, and if the permeability will change, the inductance will change. So as the temperature increases, the permeability slowly decrease, and then this will lead to decrease in the inductance value. So while designing this inductor, we have to carefully do the worst case analysis and understand that this did not lead to the saturation. Here are the few important things which we should keep in mind. The core temperature should not cross the Curie temperature. The insulation coating on the core has its temperature limit. So when we make the powder core is made up of the iron powder, which is coated with the insulation material and whose limit is 150 to 200 degrees centigrade. So it is expected that even the Curie temperature is little high, the core temperature should not go more than this, otherwise this will impact the reliability of the component and the life of the components will get reduced. The magnetic material gains its magnetic properties when the temperature is reduced if material is not magnetized. So the next important parameter is that ferrite has low Curie temperature and powder iron core has high Curie temperature. So we have to keep especially in mind that what kind of core is used in your application. Is it a ferrite core or it is a iron powder core? Iron powder core Curie temperature is little higher. So here we can go little higher limit, and then we can leverage our design little bit. The next important things is the winding temperature after core temperature. So winding temperature measurements, we need to put the thermocouples on the winding and put the inductor into the actual application and then do the measurement of the winding temperature. And for winding temperature class selections, while designing, we need to see that how our component temperature will reach, and accordingly we need to select the insulation class of the winding wires. So here are the different standards: UL 1446 temperature classes, IEC 85 classes, and the maximum hotspot temperature which is allowed under different classes. So under IEC, if your component temperature is maximum hotspot temperature limit is 105 degree, it is called class A. Under class E, it is defined as 120 degree C. Under class B, it is defined as a 130 degree C. Under F, 155 degree, and under H, 180 degree C. So based on all these calculations, we should keep in mind that which insulation class we should choose to make sure that our component work perfectly fine and it has uh, robust quality and reliability. So different class of temperature limits is having the different class which we defined as A, E, B, F, H, N, R, S. Next is the temperature estimate using power law. So how to estimate until unless you don't build the components and used actual in the system, you cannot take the measurement. But while designing, you can do certain calculations. So how you can calculate the temperature rise using the power losses. So this is the formula. It will tell you that what will be the expected temperature rise at the ambient. So delta T at B input will be whatever P loss into 1000 upon surface area to the whole power of 0.833. So by using this formula, you can easily calculate that what will be the expected temperature rise. Next things is that select the suitable core for your application. So for inductor, what are the important parameters which we need to keep in mind? So core that have the air gaps are desirable. Ferrite and strip mount core with air gap, and powder core have built-in distributed air gap like CoolMu or Megan INC or iron powder core for micrometals. For transformers, we consider the core selection as a strip material which have the highest flux density and are generally used at the frequency less than 20 kHz. About 20 kHz, ferrites are desirable because of low core losses or powder iron core. So cost comparison, of course, we can see here that in powder cores, iron powder range from 1 times to 3 times, like CoolMu range 4 times to 5 times, and high flux approximately 10 times. Okay, and MPP almost 12 times. In ferrite, F, P, R, and J material roughly equivalent to 1Y. So W material 1.25Y, 1.2, 1.75Y. H material will be somewhere 1.5 to 2 times. The ferrite cost in function of geometry. So torite, it will be very least, E core will be medium, and other shape will be most cost. So this is what the things we should always consider, that while designing any components and selecting their raw materials. So what important things we should keep in mind. So that's what we are discussing here. Then addition to number 4 selection is high magnetostrictity material create annoying audible noise. Inductance of ferrite torides decrease after winding because of mechanical stress. Custom scores are possible to get without additional cost. No need to always select from datasheets. Select proper insulation material like nylon, polyesters, which depends on the voltage, the breakdown, and the temperature limits. So ferrite core comparative geometry consideration. Here we have given the details about that: the pot cores, double cores, E cores, and ECTD core, PQ core, EP core, toride core. What will be the core cost, bobbin cost, winding flexibility, assembly, mounting flexibility, heat dissipation, shielding. So depending on our applications, we need to very carefully select, the type of the geometry so that we can get the optimum design. The design requirements of core So for power supply components, what will be the desired core characteristics like EMI filter, common mode filter, inline filter, the high permeability and high saturation. Power factor correction inductors, so here the high DC bias and low losses, and the output transformer high frequency like 20 kilohertz and above, here it is desired that low losses, and low frequency like 10 kilohertz and below, here it is desired that high saturation. Core is good for our design. So thank you, and we will discuss further in the next coming video. Thank you very much.